Audio Jungle. Audio Jungle.
Right, so here we'll talk about torsion, right? Torsion. So basically, if you say moment, because torsion is generally related to twisting moment, but you can say two things we have, which is nothing but bending moment and twisting moment. Okay, bending moment and twisting moment. So if I say moment, so moment is what basically divided in two parts. You can say it's twisting moment and it's bending moment. It's a bending moment, right? Twisting moment and bending moment. For the torsion, twisting moment is our interest. Okay, but generally if you discuss about the bending moment also in short, bending moment, and here we have a twisting moment. So if you say bending moment, then we can take one beam here. See, this is the beam, and for this particular beam it is fixed at one end, and we are applying the bending moment at the free end. This is the bending moment. So what will happen to this beam? So definitely once you apply bending moment at the free end, then this beam will deflect, or it will bend or deflect like this. So this deflection you are getting because of the bending moment. But here if you see here, that bending moment is what? Applying along axis. Bending moment is what? Bending moment is what? Along axis, if you see here. But if you talk about the twisting moment, so for the twisting moment, suppose this is the circular bar, this is the circular bar here, and obviously for this circular bar we have the axis. See, this is the axis here, you can show axis like this. So when you apply torque, so torque will be about axis. That is the only difference. Huh? Torsion is always about axis, but bending moment is what? Along axis. That is the difference only. So torsion is what? About axis. Okay, about axis. This is axis now. That is the basic difference between twisting moment and bending moment. So always remember this torsion, because we have mentioned the name torsion. So torsion is also called twisting moment, is also called twisting moment, is also called axial couple, is also called axial couple, is also called torque. Okay, is also called torque. Generally, if you for the any circular shaft, suppose this is the circular shaft here. Okay, this is the circular shaft, and if you talk about the torque for the circular shaft, then this termed as a torsion. Okay, and if it is clockwise about the axis, torque is what? Clockwise. Okay, torque is clockwise, then clockwise torque will be considered as a positive. Okay, so clockwise, then this torque is nothing but positive. Okay, clockwise it is positive torque, positive torque. Okay, and if you are writing the anti-clockwise, then this torque will be negative. That you need to remember. Okay, if it is anti-clockwise, then it will be clockwise and anti-clockwise. Anti-clockwise means something like this. See, this is the anti-clockwise. So its torque will be negative. So this is nothing but positive clockwise, and this is nothing but negative. It's a very simple sign convention. All right, simple sign convention. Now one word which is always important, that is pure torsion. Okay, that is nothing but pure torsion. So what is the mean of pure torsion? It's very important. Sometimes for 1 marks question can be asked. If you say pure torsion, so pure torsion is generally defined as a member is said to be in pure torsion when its cross section are subjected to only torsional moment. Okay, and not accompanied by any axial force or any bending moment. Means there should not be any bending moment, there should not be any axial force, because if axial force will be there, then definitely uh, that bending moment will comes into picture. Okay, so for that reason, there should not that member should not subjected to the bending moment, or should not subjected to the any axial forces. It should subjected to only torsional moment or twisting moment. Okay, called pure torsion, called pure torsion. Always remember, this is the very basic simple definition, pure torsion. Okay, so and how torsions uh, twisting movement will come into picture, that is the secondary part, and will tell you. So generally, pure torsion, in case of the pure torsion, shear force, bending moment and axial force, basically axial force will be zero. Okay, axial force will be zero. So if you talk about the uh, pure torsion, if you talk about the pure torsion, so in case of the pure torsion, these points are very important, you need to remember this. In case of the pure torsion, this torque will not be zero. Means torque will not be zero. Okay, axial force, axial force means AF should be zero, and and obviously bending moment bending moment, which is nothing but BM, must be zero. This is the condition for the pure torsion. This is the condition for the pure torsion. Okay, all right. In other way you can say, if you talk about the for the pure torsion, so only that shaft is what, in other way you can understand in this way, this shaft is what, nothing but subjected, this shaft is nothing but subjected with the T only. There is no axial loading, or there is no uh, bending moment. Only torque will be there. So this is the basically pure torsion. This is called pure torsion. All right. Now, if you say when and how that torsion will comes into picture, so that is because of the shearing stress. Okay, that is because of the shearing stress. If shearing stress will be there or shear force will be there, so definitely uh, torque will exist. Okay, like very simple example, very simple example. Suppose this is suppose the object here. See, this is the object here. So for this object, suppose this is the surface. Okay, so on this surface, suppose we have a on this surface, on this surface we have shear stress. What is that? Shear stress. So tau is what existing here. Tau is what existing here. So when tau is existing, that is shear stress is what existing. So because of the shear stress, always remember torsion will come into picture. Okay. So for the torsion, shear stress is required. So I can write here. I can write here. Torsion produces shearing stress. Torsion producing shearing stress in the section, in the in the in the section, or just opposite also. So suppose torsion is what acting, then how and where you can get the shear stress. I will show one example so you will understand. Suppose this is the shaft here, and for this shaft, suppose we have a torsion. This is the shaft now. Anywhere we can take one elemental portion, and that elemental portion is somewhat like this. See, you cut the portion, so portion will be like this. And if it is connected with the shaft, it is connected with the torque here. It is connected with the torque. Okay, it is connected with the torque here. So what will happen? See, the shear stress will come into picture. I mean, if you check any section for this particular uh, shaft, then you will get the shear stress, tau. Shear stress you will get. So the point is, if shear stress is existing, it means torsion will be there, and opposite also. If torsion is there, then any section you can choose for the shaft, and you will get the shear stress. You will get the shear stress tau over the surface. Any element you can take. Okay, here I have taken these elements. So for this particular element, see, this is the one portion you have taken for the shaft. So if you see this shaft, because this complete shaft is what connected with the torsion. So if you see this particular element, so this particular element will be subjected with the shear stress. So the point is what very clear. If torsion is what existing, it means shear stress is what existing. Or if shear stress is there, then definitely torsion will be there. Okay. Another example also I will give to understand this, but this one is very clear. Okay. This is the tau, basically complementary shear stress. Now, simple example you can see, suppose this is the wheel. This is the wheel now, okay? And this wheel is what at this, about this point, this wheel is what about to rotate. But when it will rotate, when it is suppose connected with the, this basically a shear force, you can say. If this shear force F we have, huh? Then this perpendicular distance R we have. So what is the torque? Torque is nothing but F into R, right? So basically this F will be what? This F is nothing but shear force, right? And how this shear force will appear? It is because of the shear stress also, you can say, because if you see the shear stress is nothing but shear stress, it's a tau. Shear stress is nothing but It's nothing but shear force divided by surface area divided by surface area. Shear force or tangential force. Huh? Tau is nothing but shear force. Tangential shear stress is nothing but also called tangential stress. If you talk tangential stress, so tangential stress is nothing but tangential force divided by, and this tangential force also called shear force. This tangential force divided by area. So basically, this force is what tangential force. If it is existing, so definitely shear stress will be existing, and obviously once force came into picture or shear stress came into picture, so torque will be existing there. That's the point actually. Okay, now this is the one thing. Second thing, if you go for the you know that derivation of the torsion formula, so it's very simple. It's very simple. We can have this something like this. Now we are going for the torsion formula. This is the derivation. Okay, this is the derivation. And now in this case we can take torsion formula. Here I will write torsion formula. Now we have one circular shaft. It is fixed at one end. Now for this particular torque shaft, we have cross section of this shaft, which is nothing but circular. The circular shaft here. Okay, right. Now you can have one axis, and that axis is nothing but reference axis basically. Okay, something like this you can take as a, this is the longitudinal axis basically. Now if you along this, if you apply the about this, sorry, not along, about this axis, if you apply torque, this is the axis which is nothing but uh, longitudinal axis. If you apply torque, so it means, what is the meaning of it? It means over the surface of this shaft you are applying the torque. Then what will happen? I can take, see, this is the fixed end, and because this free end is what this end, which is nothing but A, and here it is B, the complete length is nothing but L. So end A is what fix, end A is what fix, and end B is what free. So if you apply torque, then obviously free end will rotate. So now I can take, this is the point A. Okay, once you apply the torque, it will rotate, and you may get something like this. Okay, so now this is what A dash, right? You can say this is nothing but A dash. Anywhere you can take. So definitely here also you will have an angle, and here also you will have angle. This is phi, and this is what? Theta. Phi and theta approximate, it is same. Okay, always remember, phi and theta approximate, it is same. It is same only. Now point is, as I told you, derivation is not important, and for the derivation you can go through my recorded videos. Reference is available. If you see the point, this phi, this theta basically, so this theta is called as, angle of twist. It is very important. Okay, in examination they are asking angle of twist. Okay, angle of twist, which is nothing but theta. Theta is nothing but angle of twist, which is important for us. Now ultimately if you derive and if you see the final formula you will get here, torque you have applied, and obviously once I have told you, once torque T you are having, then definitely shear stress will also you will have, tangential stress or shear stress tau you will have, huh? So I'm not going to derive this formula. I just want to put direct relation. L is nothing but length of the shaft. Okay, so full derivation already it is available, you can go through my recorded videos. Okay, now if you go for the final formula, then you will have T by J. This you need to remember, which is very important. T by J, tau by R, it's equal to Z theta by L. That's all. This is the main formula that you need to remember. Okay, right, I will write each and everything here. For the circular section, we have to calculate polar moment of inertia. So T is nothing but torque applied. Torque applied. J is nothing but polar moment of inertia. Polar moment of inertia, which is nothing but I ZZ, and that I ZZ is nothing but I XX plus I YY. Okay. Then tau is nothing but shear stress. R is nothing but radial distance. Okay, small r is equal to capital R on the surface of shaft. No, you can understand this. It's very simple. If I draw the side view of this, so for the side view, this is the axis now. So you will have a cross section something like this. Okay. So if you see what is the small r, so small r is nothing but radial distance. I can take one small r radius. Sorry, I can draw one radial element, and obviously if you see the derivation, so I have taken this radial elements, thickness of dr, and the radius from the center it was small r. But if you check the radial distance from the surface, so this is the capital R. So capital R is nothing but radius of the shaft. Capital R is nothing but radius of the shaft. Okay, and small r is the radial distance for the that element. So obviously small r will be capital R once you are talking on the surface of the shaft. G is nothing but modulus of rigidity. Okay, theta is nothing but it's a twisting angle, or it is also called angle of twist. Okay, and J is nothing but polar moment of inertia, that is okay, but I told you IZZ, which is nothing but IXX plus IY. If you see, this is what circle. Okay, for the circle, suppose diameter is what, capital D, XX and YY. Okay, and here the diameter is nothing but capital D. So IXX is nothing but, because it's a circle, so it's a pi d by 4, 64. IYY, that is moment of inertia, it's again pi d power 4 by 64, because it's a circle, so diameter will be same. If you solve, then polar moment of inertia for this circle or circular shaft is nothing but pi d to power 4 divided by 32. That you need to remember always. Okay, it is called polar moment of inertia. Okay, and yes, each and everything I have written. Now you always remember, okay, due to torsion, shear stress is developing between the layer. Okay, always remember, due to torsion, shear stress is developing between the layer. The the maximum shear stress is between the outermost thin layer and layer below it. Meaning is very clear. See, how you will reach to this analysis? Very simple. If I show you the tau value, huh? Tau value previously here you can see tau by r, which is nothing but g theta by l, or tau by r, which is nothing but t by j. Huh? I'll show you this formula. Any formula you can take. Like I'm taking the first combination, t by j is equal to tau by r. Hmm? What is tau? Tau is nothing but t by j into r. Torque applied is what? Constant. Once section is defined, diameter will be defined, circular section is defined, so diameter is defined, means j is also constant, so tau is nothing but directly proportional to r. If I say where will be the maximum shear stress, so you have to say where will be the maximum shear stress? Tau. So tau max always you will achieve when small r becomes capital R. It's very simple. So I can say tau max is nothing but t by j into small r becomes capital R. That's all. Because see, what is the variable here? Small r. So if I say tau max is, so small r will be maximum, and what is the maximum small r? That is nothing but capital R. That already I have shown you that diagram. This is the circle. From the center, this is the radius. From the center, this is nothing but a small r, right? So where is the maximum value of small r? So that will be the capital R. That is the surface. That is the surface of the shaft. Simple. Okay. Now, all right. So one more thing I just want to tell you. Just like a section modulus we have. Okay. Similarly, we have a polar section modulus. And how to get that polar section modulus? It's very simple. See, the same formula I'm analyzing, you just focus on it, you will understand. It's very simple. Again, the same formula I will take. T by j is equal to tau by r, g theta by l. Okay. Now see, if I say polar section modulus, so what is the polar section modulus? Polar section modulus, it is denoted by zp. Zp is always defined by j divided by r max. It is nothing but polar section modulus. Just like a section modulus in case of bending moment, it was I by y, if you remember, I by y. Similarly, polar section modulus will be zp, j by r. And if you see the formula here, t by j, check, t by j is equal to tau by r, right? I can write this, t is equal to tau into j by r, I can write. Yes or no? So basically T, which is nothing but torque, see again, torque, tau is the shear stress, and in bracket what you got, see, in bracket you got J by R. J by R. Okay. So this J by R, tau into this J by R is nothing but ZP, which is nothing but polar section modulus. Okay, polar section modulus. See, this is very important for single marks question. They are asking from the formulation only. I told you that derivation of this formula is not important at all. Once you get the result, this formula, that application is very important. And derivation, as I told you, I'll give the reference, my reference video, recorded video. You can go and watch. They will understand the derivation. It's very easy. Now this torque is nothing but, T is nothing but torque, and which is also sometimes called strength uh, in torsion, that is denoted by T. Okay. Now our twisting moment. So this T, if you see, T is directly proportional to ZP. Once tau, which is nothing but shear stress, is what constant. So you can say T is directly proportional to ZP. Meaning is very clear. If ZP is increasing, that means strength in torsion will also increase. That's the meaning of it, right? This is very important. First point. Second point, what is the mean of the another term which is here in the formula, this g theta? That also very important. J also we can write. See, I will show you this formula. The same formula I will write. There we are analyzing this formula. Okay, so each and every points whatever I am writing here, you just listen carefully, so you will understand. Again, I will write this formula. I told you, if ZP, which is nothing but polar section modulus, if it is increasing, then T, which is nothing but torsion, or you can say strength in torsion, will be increasing, because T is directly proportional to ZP, right, for constant shear stress. Number one. Number two, what I want to tell you, if I write the same formula once again, T by J is equal to tau by R is equal to Z theta by L. We can write like this. If you check this, T by theta, we can write like this. T by theta is equal to, first we had taken T by J is equal to tau by R. We had analyzed this one, first one only, first part we had taken this one. Check. We have analyzed this. This is the first part, no? See, this is the first part. And the second part also we can make a combination, T by J is equal to G theta by L, or tau by R is equal to G theta by L. We can make combination, no? So now I am making combination T by J. I need to write, no? I need to write T by J. T by J is equal to G theta by L. So what we will have, a T by theta is equal to Gj by L. Okay, now listen. In this formula, what is this Gj? This Gj is called as torsional rigidity. What it is called? Called torsional rigidity. Okay, torsional rigidity. Now what is the mean of it? So that meaning is very clear. T by theta, see, is equal to Gj by L. Now in this formula, if Gj, which is nothing but torsional rigidity, Gj, if this Gj is what increasing, that means, that's meaning is what? Rigid shaft. First point is it's a rigid shaft. If torsional rigidity increasing, then it's a rigid shaft, and obviously rigidity of the shaft will be increasing, because Gj is nothing but torsional rigidity. I am saying torsional rigidity increasing, it means that rigidity of shaft is what increasing. That is one thing. Second thing, at the same time, if GZ is what increasing, if GZ is what increasing, so definitely at the same time stiffness of the shaft is also increasing. Stiffness of the shaft is also increasing. Okay, what is the stiffness of the shaft? So stiffness of the shaft is nothing but T by theta. T by theta is nothing but stiffness of shaft. Okay, so if GJ is increasing, then T by theta will also be increasing. Yes or no? If T by theta is also increasing, so that means stiffness will also be increasing. All right. And obviously, this will be possible when this condition will be possible when theta, which is nothing but twisting angle or angle of twist, is what decreasing. Okay, so whenever GJ is what increasing, okay, or rigidity of the shaft is increasing or stiffness is increasing, that time, that only you will achieve when theta, which is nothing but angle of twist, is what decreasing. That is very important. You need to remember, this is the analysis of the uh, this torsion formula. It's very simple. This is the analysis of the torsion formula, that's all. Okay, now coming to the next analysis, as I told you, because formula is important. And first point, second point, how to use this formula and each and every term in the formula, that also very important, that we are doing here. Okay, that we are doing, and it's very very important. This polar moment of inertia, whatever I have calculated, uh, polar moment of inertia, definitely it will be different for different case of the shaft. Maybe solid shaft, then polar moment of inertia will be different. Maybe it is hollow shaft, so polar moment of inertia will be different. That is the another point we have to discuss later. But here, what you got here, that basically analysis of GJ, that is nothing but with a GJ increasing, then stiffness increasing. And this is one important point. And another important point is here, see, if ZP, which is nothing but polar section modulus, if suppose it is increasing, then obviously the strength in torsion will also be increasing. That 2 points need to remember, it's very important. Okay, maybe sometimes you may able to find that relation also, and that relation is what basically like uh, to calculate torsion with the help of angle of twist. So that is called torsion test. Okay, that is also called torsion test. So that test and all, it is not uh, going to ask in your examination. Simply that formula based problem will come, but in like in semester and all, that torsion test and all there, but in your gate syllabus it is not there. So better you just leave that portion, not required. Now what is the next one, what is the next point which is important? That is nothing but the uh, connection of the shaft. Okay, like how to connect the shaft, that is very very important point we need to discuss here. That is also very important, and they are asking in examination. So this is called connection of shaft, or better you say arrangement of shafts. Okay, arrangement of shaft. So up to here, this is related to the formulation only, so that point is clear. Now coming to the arrangement of shaft. Okay, coming to the arrangement of shaft. Arrangement arrangement of shaft. So basically two types of arrangement we have here. Okay, practically what we are using, two types of arrangement we have here. It's nothing but series. Okay, it's nothing but series, and another one is parallel. Another one is parallel. Okay, series and parallel. So that is very simple actually. If you see one end of the shaft is what connected with the another end of the shaft. So it's nothing but what? It's a series, just like a resistance. One end of resistance is what connected to the another end of resistance, then becomes series. And when the all, suppose more than one shaft are there, but all shafts ends are connected at the same point, okay, so that will be called as a parallel. Simple. Okay. So now coming to the important point, what is the important point that we have to see here? See, if I say series connection, okay, if I say series connection, so in series connection generally one end is what connected with the another end, meaning like if I show something like this, I will show by this diagram. Many diagram are available, anyone you can take. Suppose this one I'm taking. Suppose one shaft we have, and here it is connected at the fixed one side, it is fixed, and then this another end is what connected with the another shaft, and at the same time this end is also connected with the another shaft. So three shafts we have basically. Okay, if I say this is A, this is B, this is C, and this is what? D. Everywhere we have a torque. Everywhere we have a torque. And if you check, just say here the torque is nothing but uh, any direction also you can show, but I want to show you the arrangement. Later on I will tell you like how the torque will be added and what will be the constant, what will not be constant. That is the secondary. I just want to show you the arrangement. So this is the series arrangement, and how you can show the parallel arrangement, that is important, no? So parallel arrangement, as I told you, you can say one shaft is what inside one shaft is what connected at one end, and another end is what connected or fixed at another end. But at the same side, at the same time also I can tell you, shaft is what one inside other, one inside other, meaning is, suppose I just want to show you this shaft. Okay, I just try to understand this two ends we have, and it is fixed. It is fixed. See, listen carefully. I just want to tell you, suppose this is the one shaft here we have. This is the one shaft. And another one more shaft we have, which is inside of this shaft. So see, for both shaft, both ends are same or not. Yeah, that's I wanted to tell you like this. Two shaft we have. Okay, one is, you can say, A, B, C, D. This is the one shaft. Another shaft is nothing but P, Q, R, S. See, both are fixed at the same ends. Now if you check, this another one is called parallel shaft here. Okay, so it's very clear point, because one is what, one shaft is what inside another shaft. So definitely once you apply the total torque here, then this total torque will be distributed in both, no? So if I say total torque is what applied capital T, so one shaft which is outer, if suppose it is sharing T1, and inside another shaft it is sharing torque T2, then total torque T applied T is equal to T1 plus T2. That is the analysis I'm saying. Okay, that is the analysis I'm saying. Anyway, so hope this one is very clear. Series and parallel. Series and parallel. Hope this one is very clear. Okay. Now, so now it's a time to write the formulation or the difference between series and parallel. With the formula also it is very important to write. So first I will write series. For series I will show you what are the formulation. Series shaft. Series shaft. Okay, now for the series shaft, see, In case of the series shaft, if you check whatever the torque we are applying here, see, I will show the diagram and easily you can understand. It's very easy. At one end it is fixed. See, this is the one shaft. Here we have another. Okay, next end-to-end connection, it becomes series A, B and C. I can write like this. Now if I say angle of twist, because two things we have here, one is torque, another is angle of twist. So in this situation, if I say what is the total torque, because torque we are applying for this particular case, here also and here also we are applying torque. Both places we are applying. Okay, both places we are applying the torque. But now if you see the angle of twist also we have here. What is the angle of twist? I can say theta AB, that is the one angle of twist here for this section, and theta BC, which is nothing but another angle of twist. Another angle of twist. So whatever the torque here applied, this is what, just say T1 and this is what T2, right? So my point is, because one end is what connected to another end, so whatever the torque you are applying for the first section, the same torque will, because here it is rigidly fixed, here we are not getting any slip and all. At point B it is fixed. So whatever the torque you are applying at end C, the same torque will be shared to the end B also, and the same torque will be shared to at end also, in A also, because all points where it is connected to each other, it is fixed. We are not having any slip and all. Okay. So in this situation, easily we can say whatever the torque we have here, all the torques are same in case of the series connection. T1 is equal to T2 is equal to T. That is the point one. Second point, what about the angle of twist? Check. What about the angle of twist? Obviously, because angle of twist, as per the length of the section, as per the material, what material you have used, so definitely G also will vary. So if I go and calculate the total twist, angle of twist, so total angle of twist will be nothing but theta. Okay, and this theta is nothing but completely for the from end A to C, and it is nothing but theta AB plus theta BC. This is all about series shaft. This is all about series shaft. If I say theta AC, if I say theta AC, so theta AC means what? It's the theta A minus theta C. That's the mean of it. That's the mean of it. Okay. Always remember. Similarly, theta AB is nothing but theta A minus theta B. Similarly, theta BC is nothing but theta B minus C. And that is the way to write. Any end, suppose it is fixed, like here end A is nothing but fixed. End A is fixed. So what is the theta A that time? It will be 0, because this end is what fixed, so there is no deformation at all. This is all about series shaft. Now coming to the parallel shaft. So what happens to the parallel shaft? So it's just opposite to this parallel shaft. Parallel shaft. As I told you, in case of the parallel shaft, one shaft is what inside another. Like this. So outer side shaft is nothing but Different color I'm using, so it will be more clear. Right. Now, if we say, obviously, uh, here it is sharing torque T1 and inside it is sharing T2. If I say total torque applied to this shaft is nothing but capital T. So the total torque T, obviously, once you apply, then inside shaft will resist this shaft by T2 and outer side shaft will resist by T1. So total resistance provided by the shaft, because capital T is the external torque applied, so it will be equal to T1 plus T2. Both shaft will try to resist. So it's nothing but T1 plus T2 is equal to capital T at equilibrium condition. Or you can say whatever torque you are applying for this parallel shaft now, so it will be shared in two shaft, because inside we have a two shaft, right? One inside other, we have totally two shafts, so it will be distributed T1 plus T2. We cannot say equally distributed, because definitely both shaft will have a different radius, different diameter, different maybe material also sometimes. So I cannot say both are sharing by the same amount. No, the sum of the total torque T1 plus T2 will be equal to external applied. This is the condition one. This is for the parallel shaft. Now, what about the twisting moment? I say AB. So definitely AB for outer one and CD for inner one. So there is no doubt, because both are fixed at the same end. So we can say theta AB is equal to theta CD, or is equal to theta, or is equal to constant, means your angle of twist for the parallel connection, it's constant. Once it is constant, then how to perform the calculation? It's very easy now. What is the formula? If you see, T is equal to T by J is equal to Z theta by L. So theta is constant, means theta is equal to what we can write, Zj by TL, if I'm not wrong. Huh? No, theta is nothing but TL by Zj. Sorry, it's nothing but theta is nothing but TL by Zj. I'm saying both angle of twist AB is equal to theta of CD. That I have written. See, L is what constant, no doubt, because length will be same for both, because both are fixed at the same end. So L will be cancelled out, but theta AB, but T torque will be different. So first inside AB torque, AB shaft will AB shaft is what, external shaft. It is sharing by T1. So T1 divided by uh, maybe material is what it is made by some different material, so G1, and polar moment of, because diameter will be different, so J1. Similarly, it's T2 by G2 G2. So this is the one another relation. And how you have achieved, it's by the same way, like you have equated the twisting moment. So this one or this one meaning will be same, because if you are writing this, that meaning is what same, just like what I have written here. Huh? This is all about the series and parallel shaft. Okay, series and parallel shaft. So I think for today it's enough. We'll solve few problems in next class related to this. Okay.